All right, welcome everyone to our Thursday Astrophysics IAS seminar. Today we're very happy to have one of our own, Giovanni Cabass, who got his PhD from the University of Rome, La Sapienza, in 2018. Spent some time as a postdoc at Max Planck Institute for Astrophysics and has now joined us here at IAS. So Giovanni works on inflation, on effective field theory techniques, on observable imprints of inflation, on things like galaxy clustering. And today we will hear about the zoology of graviton, non-Gaussianities, and inflation. So please take it away.
Thank you, Susan. Yes, so I'm going to talk to you about this topic that I've been interested in the last year or so, and this about graviton non-Gaussianities during inflation. So the title Zoology hopefully will become clearer now when we go to the outline. So I will first start by discussing some motivations on why I'm interested in this graviton non-Gaussianities, in the sitter essentially. And then, more precisely, what I'm interested in is looking at two graviton non-Gaussianities in models of inflation where the isometries of the sitter are spontaneously broken. More precisely, the case where boosts, the sitter spatial conformal transformations are broken. And to study these different scenarios, what I use is this paper essentially by these authors, 2015. This called Zoology condensed matter, where they study how instead of breaking the sitter isometries, you can break the Poincaré isometries, precisely Lorentz boosts. So this will form the basis of essentially my talk, and this is where the zoology comes from. So as I said, these authors try to derive the different ways in which the Lorentz boosts are broken. Then so they work in flat space. Then what we want to do when we work, we want to look at inflation. Then we want to actually couple the system that they study to gravity. So this is what I will do then: couple the results to gravity and see the different scenarios that they study, whether or not they can sustain some inflationary solution, and also whether or not, it's an interesting question, whether or not the different scenarios can actually also exit inflation. Not all of them will be able to, so this is really interesting to check. Then I will actually go to the main part of the talk, which is look what are the different graviton interactions in these different scenarios that one can have, different ways which the sitter boosts can be broken, and discuss some phenomenology for these interactions. And then we'll conclude. So, okay, some motivation. So I don't think there is any better way to say it than this. Essentially, this citation from this work, 2015. Essentially, we hope that inflation, we hope that really it is happening at a very high energy scale, could be as high as 10 to the 14 GeV. And if that's the case, we will really, by looking at the inflationary observables, we'll really be looking at some possibilities that can happen on some energy scale that is not, it is far higher than what we could achieve in modern day particle accelerators and also in any foreseeable future. We know that any interaction that happens during inflation then that gets imprinted on cosmological observables, more precisely gives rise to what we call primordial non-Gaussianity, that is left imprinted into, like, for example, CMB statistics, cluster structure, and so on. So literally, we have some sort of like cosmological collider that we can look at. So now let me go in more detail. So for us, inflation indeed is this epoch of accelerated expansion and then smoothly connects to the Big Bang. So there are many questions one can ask: what happens for interaction during inflation? So one thing that one can ask is, what are the signatures of new particles that are present, depending on what is their mass of the particles, on their spin, and so on. And this is essentially the program that the paper that was citing before is kind of advocating. Now, a difference, however, with the lab case, colliders like ADC and so on, is now indeed we're not in flat space, but we're in the sitter. And an interesting lesson that we've learned from many studies, for example, studies of the effectivity of inflation and so on, a large amount of literature that will not summarize here, But what we have learned is that some phenomenologically interesting case is when we look at the case where indeed these isometries of the sitter are broken. The special chromatic transformation precisely of the sitter are broken. So this gives rise to some phenomenologically interesting results. So this is another way in which you can attack this problem, and this is what I will do. I will not look at what are the signatures of new particles. I mean, this is obviously a very interesting question, but this is not what I'm interested in here. But I will look at all the consequences of the different ways in which these isometries can be broken. So why focus on the graviton then? Because now we are breaking some symmetry, some global symmetry, and we know from particle physics or from field theory that whenever we break some global symmetry, some Gaussian mode is present. There can be many of these in principle, and so a complete analysis of all the possible interactions and the resulting Gaussianities can be complicated in general. So this is why I focus on the graviton, because things are simpler there. It is easy to focus on it, and still you can have an idea what you can obtain in different cases, and still give you an idea what are the different signatures. Finally, an interesting reason why I look into this, is that there have been some recent developments in what is called the cosmological bootstrap program. So what is this bootstrap program? So people essentially try to find some set of rules to obtain correlation functions, inflationary correlation functions, without referring to a specific Lagrangian, but just have some rules to write them down. And this is a program that, for example, this is a reference. I mean, there are many others. I'm not making any justice to all the literature here. But what's something that is interesting is that recently, this bootstrap approach has been extended to the case where indeed these boosts of the sitter are broken. So this boostless bootstrap by this reference by Enrico Pairi in October. And however, in this reference, only one particular symmetry breaking pattern has been studied, the one precisely with single clock inflation. So it is interesting to look at what are the consequences of the other patterns, just also because working on the level of the Lagrangian, as I will do in this talk, still can give you some help, for example, in guiding you into deriving the bootstrap rules, give you some idea what you should look for. So this is also something that for which these results can be useful. And finally, of course, in the case that we will detect harmonic gravitational waves in the next generation experiments, this would be great. And having classified the possible interactions that we have for the graviton and so on, and the signatures, I mean, this can be very exciting if we detect them, because we could start to constrain these interactions. Okay, so this was for the overall motivation. So let us go to this review of this zoology of condensed matter paper. So as I said, we want to see the different ways in which we can break the sitter isometry, the sitter boosts. Instead of doing this by the start, we can just try to build some intuition by working sub-horizon scales, where we know that the sitter boosts, which are special chromatic transformations, reduced to Lorentz boosts, and the sitter dilations reduced to time translation. So I end up with a Poincare Lie group. And then I can just work with it and just trying to understand what are the different scenarios in that case. And this is what these authors do, 2015. They try to look, they classify all the symmetry breaking patterns that are associated with an homogeneous and isotropic medium, but also a static medium. So the requirements of homogeneity and isotropy here are hopefully clear. Like in cosmology, we always want to deal with some background which is satisfies doesn't break rotation and translations. But let me spend some words on the staticity requirement. This may be a bit unusual, or could be a bit more difficult to understand. So the simplest way I could come up with to understand what this statistical requirement is just by an example. you can think about a scalar field that I call pi here. And for example, in single field inflation, this pi is literally related to the comoving curvature perturbations. So now we are breaking Lorentz boost, so we can have a speed of sound, Cs. And in principle, these boosts can be broken strongly, so we can have a strong breaking of them. So the speed of sound, in principle, can be very small. So this parameter here can be, in principle, very, very large. The requirement of staticity, instead, is essentially tells us that the speed of sound is almost constant in time, so it won't vary a lot in unknowable time. And this is kind of good. We usually want this in these models of inflation. We don't want the parameters that describe the fluctuation to vary strongly in time. So this is a way to actually enforce this. So this is essentially the requirement of staticity. So then let's go to how we actually obtain these different symmetry breaking patterns of Lorentz boosts. So what we have to look at is essentially the different generators for space-time transformations, but also generators for essentially that govern the collective excitation of our system under consideration, which can be the total Hamiltonian of the system, total momentum, total angular momentum. And so these are the ones that we assume to be unbroken. So staticity, translations, and rotations. Essentially, our current state is invariant under these. Now, the different symmetry breaking the different patterns that we can have amount to ask whether or not these unbroken generators are equal to the space-time ones or not, or there is some internal symmetry, Qi, Qi, and Q tilde I, that makes them different from each other. Whether or not these internal symmetry generators are zero, whether they are zero or not, this will determine the various systems that we have. So an interesting point that I make here, just for clarity, is that, well, just to make also justice to the original work, is that I will assume that the generators Qi and Q tilde I, assume that they commute with the spacetime generators. This is not required in general. You could have them not commute with the spacetime ones, and this indeed is actually one of the main points of the paper of 2015. They try to look at what happens if these do not commute. You end up with some medium that they call Galileid, which is interesting in itself. However, it is difficult to couple it to gravity. This is my understanding. So I didn't really investigate it. I just assumed that there is a commutation of the generators with these, and then things are simpler. Okay, so given this clarification, let's go to what are the different cases. So I will discuss the different here the different systems. What are the generators in all the different systems, and also what are the order parameters for the system, and also what are the Goldstone fluctuations on the last column. So the simplest case that we have is that of a superfluid, where the only internal generator is this charge Q, which I think, my understanding, you can think of it as like essentially to count the number of particles that are present in the ground state. And the other Qi and Q tilde I are equal to 0. So the order parameter in this case is you can essentially some phase field psi of x that has an expectation value in the vacuum that is proportional to a time coordinate. And in this case, you have only one Goldstone fluctuation, which is the fluctuation of this field here. So you have this pi field. Then you can do some more complicated example, which is the one of solids and fluids. So instead of really, I will use the word solids in the rest of the talk, but more than solids, you should think like not some crystal, but more like some jelly, because I want to have some preferred access in my solid, like I mean, I will have full rotational invariance, but still, I will use the word solids because this is what is done in the literature essentially. So the generators here are the non-zero internal generators are Qi and Q tilde I, and the order parameter you can think of it as a triplet of scalar fields by I that the vacuum has an expectation value proportional to x. And the fluctuations, there are three of them, and just a fluctuation on these fields. So to have maybe more intuition on what these fields are, you can think of phi I as the Lagrangian coordinates of the volume elements of your medium, while xi are the Eulerian coordinates essentially. So this, as I said, was requiring this. Sorry, this symmetry breaking pattern describes both solids and fluids. Fluids are just essentially a more symmetric version of solids that they essentially we have to enforce this particular symmetry here that make sure that for fluids only compressional modes matter. And essentially is a symmetry under internal diffeomorphism in Lagrangian space essentially that preserve volume. So whenever you require this symmetry here, you end up with a fluid. Okay. Then what are the other systems that one has? There are some combination of these two, which is this finite temperature superfluid. I'm not an expert on condensed matter, so I'm just a bit treading what the original authors did. This finite temperature superfluid seems to me to be a superposition of a superfluid in itself plus a normal fluid, and all the generators are then non-zero. So you have Q, Qi, and Q tilde I, and the order parameters now, instead of having 3 scalar fields, you have 4 of them, and the value proportional to the spacetime coordinates, and you have 4 Goldstone modes in this case. So since we see that this essentially is literally just the superposition of the other two, the combination of the other two, I won't discuss this a lot in the following because just discussing one, the other two separately is enough. Then let's go to the final two. Essentially, we have what they are called, what the authors called feramids. We have type 1 faramid and type 2 faramid. Type 1 faramid is actually the simplest of these symmetric patterns because all the internal symmetries are 0, so you don't have Q, Qi, and Q tilde I. And you can think of it, I think of this as like some sort of ether where there is some vector field a mu which has some expectation value non-zero proportional to the Kronecker delta on the background. So what are the Goldstone modes in this case? In this case, the Goldstones are essentially the rapidity of some Lorentz boost that you can make on this expectation value. The rapidity has 3 components. It is a vector, and so we have 3 Goldstones in this case. Then we have a type 2 faramid, which is similar to the other one, but instead of having one vector field, one time-like vector field, we have a triplet of space-like vector fields, which have this valve. The number of Goldstones here now is 6 and not 3, because we both have the rapidity of a broken boost that we can make on this background, but also we can make a rotation. So we have 3 Euler angles. So we have 6 Goldstones in total. But there is actually a final case, which is this type 2 superfluid. What's called this type 2 superfluid, which essentially is a superfluid, but also it has some spin degrees of freedom within a relativistic limit. And my understanding is that you can describe this by having a superfluid with some type 2 faramid on top, and this faramid in a relativistic limit would play the role of this spin. So describe this spin. Okay, so these were the systems. And let's go to the coupling to gravity. So there is a well-defined prescription, well-defined, not prescription, well-defined technique to actually couple these systems to gravity. This is called the CCWZ construction, Callan-Coleman-Weston-Zumino construction. You would use this construction to write down your Lagrangian for the Goldstone modes that I discussed above, and then you would essentially, my understanding of it, you would gauge the Poincare group, and this would essentially introduce gravity. So this is the full construction one would do. It's complicated, however, so I didn't do this, but just realize essentially that we're either dealing with some preferred coordinate system here, in the case of superfluids and solids, or with some preferred frame, in the case of the feramids. So essentially, when we couple this to gravity, we are either breaking the gauge symmetries of gravity would be the diffeomorphism invariance, in the case of superfluid and solids, or the fact that we also have local Lorentz transformations as a symmetry in the case of feramids. So this kind of intuition, this kind of statement, if you want, is kind of is bolstered by the fact that in these authors, in these papers, they explicitly did the construction, this constant construction for the superfluid case and for the type 1 feramid. And you can indeed show that this is what happens. You either break time diffeomorphisms in the case of the superfluid, or you break local Lorentz boosts in the case of feramid, type 1 feramid. So now, we are breaking these gauge symmetries of gravity. So whenever we break some gauge symmetry, we end up with some additional degrees of freedom in our system, which indeed are the goals that we were discussing so far. So what we can do is then, whenever we introduce gravity, we can then use the broken gauge transformations to make the metric eat the degrees of freedom. And this is what is called going to the unitary gauge. So we don't anymore have some matter fields, but these are just eaten by the metric. And then this makes easier to write down the different objects that we can write down in our Lagrangian. So let us then go to this unitary gauge where there is no anymore any Goldstone, but thus everything is in terms of the metric, and see what are the objects that we can use in the different scenarios. So as I said, let's go as before. We have the different cases. We have a superfluid, and here now, what are the unitary gauge variables in this case? So obviously, in unitary gauge now we can write anything that is invariant under time diffeomorphism, which is a metric. So anything constructing from the connection, so curvature tensors and so on. But we can also indeed use the time coordinate itself, because time diffeomorphisms are now broken. So we can use this more precisely. We can use essentially the derivative of the time coordinate, which is some sort of projector over some surfaces of constant time. So these are the variables, and anything you can build out of this, you can use. So these are the variables in this case. Then let me go to the case of solids and fluids. The situation is similar now. Instead of breaking instead of breaking time diffeomorphisms, now we're breaking spatial diffeomorphisms. So we can again take everything that is constructing from the metric, but also use these projectors essentially, which are projectors, if you want, that are orthogonal to the word lines of the fluid elements, if you want. Now we have spatial indices in the game, and everything is fine as long as we contract them in a way that is rotationally invariant. So these are anything that you can construct out of this is a fair game in the case of a solid. Then let's go to the feramid, type 1 and type 2. Now the variables here are, instead of the space-time coordinates, will be the basis in the tangent space at each point in space-time. So the tetrad that I call A mu. In the case of type 1 pyramid, we can use the time-like vector, the time-like component of the tetrad. While in the case of a type 2 pyramid, we can use the space-like components. So we have 3 of them. And again, here we have some spatial indices. And again, everything is fine as long as we construct them in a way that is rotationally invariant. So now we have these two kinds of feramids. I will not, from now on, discuss a lot type 1 anymore. The reason is that whenever you have, the reason is the fact in 4 dimensions, whenever you have a triplet of vectors which are normalized and orthogonal to each other, so you have like a dry bind, you can immediately write down the 4th component and obtain the full tetrad by using the volume form. Essentially, you can write down the 4th vector in this way. I mean, this is just some technical construction, but you can do it, and you can check that this vector is normalized to -1, and also is orthogonal to all the others. Essentially, then whenever we can just work with this, we immediately have also the last one, and one can check that also this vector transforms as it should under local Lorentz transformations. You can check that first is invariant under rotations, as it should, just because the indices are contracted in this way. And you can check also that under a boost it transforms as it should. So essentially, we can just forget about the type 1 pyramid and just work with the type 2. The type 1 is just a subset of it, where essentially you can impose some sort of symmetry to single out just this object. So then we essentially have 3 cases to consider. So before going to the graviton interactions, I still wanted to mention a bit. So we want to check whether or not this different system can sustain inflation. So an epoch of the Sitter expansion, and then also if they can exit from it. Because
Giovanni, can I ask a question? Just
yes,
to help my intuition, and maybe this is something you're going to get to, in which case just say that. But when I think about the the observable impact of departure from de Sitter, the main one that comes to mind is tilt of the primordial spectrum, because there's an end, the expansion isn't perfectly exponential and towards the end of inflation. So is that effect something that fits in this language? And if so, how? Or is that a different kind of effect from what you're talking about?
No, it fits. Like the fact that these two, I will jump a little bit forward. The fact that these two, the case of broken time diffeomorphisms, so the superfluid, and the broken spatial diffeomorphism, they can have actually they can have deviation from the Sitter. Then this allows you to get a tilt, as you were saying. Okay. The fact that indeed, I will just jump quickly forward, that for a pyramid you can actually only have x of the Sitter, then you wouldn't be able to get that. So from this point of view, a pyramid would not be a good way to actually build a realistic model. But I will maybe go back to it in a moment. But your question, regarding your question, yes, you can have deviation from the Sitter, and this will indeed give you the tilt of the spectra as in the usual case. Yes.
Good, thanks.
Okay, thank you for the question. So let's check indeed whether these systems can sustain the Sitter, and then if they can exit from it. So the case of broken time diffeomorphism, so the superfluid case, this has been studied in just the case of the effectivity of inflation. This has been studied a lot. So this we know that this is fine. We can have the Sitter. We can actually also we can deviate from it, and we can also exit inflation, because we literally have some clock that tells us when inflation ends. So that's very good. So this is everything fine. Now, what happens to the case of broken spatial diffeomorphisms? So in broken spatial diffeomorphisms, the case of the leading action is the action of solid inflation, this model of 2012. And also here we can have an epoch of quasi-de Sitter expansion, and also we can exit from inflation. Let me go into this a bit in more detail because maybe this is less fun. People are a bit less familiar with this, but also because it allows me to introduce some variables that they will come back later. So in the case of a solid, the solid inflation, the action is this. So we have Einstein-Hilbert part. Then recall that now the variables that we have in unitary gauge are the metric, and also we can use the projectors, the mu xi. So these we can use. Then when we have these projectors, what can we do? A leading ordering derivatives, we can just then contract them with the metric itself, and we can build then up the spatial metric with upper indices. So this is the variable that we can have. And then we have to contract the indices in a way that is invariant of the rotations. Luckily, there is a finite number of rotational, this is something I learned from this paper, actually didn't know. There is a finite number of rotational invariants that you can write down. Everything can be written in terms of traces, trace of the metric, trace of the square, and trace of the cube of the metric. So in general, you can write down a generic function with these variables x, y, and z, and this is you're done. Now, let's see how we get the Sitter, actually approximate the Sitter. So we have some sort of epsilon variable that is different from 0 and tells me how close I am to actually exact exponential expansion. How can we check what allows you to get this? So we realize that the only variables here that are the only variable that is not invariant under a scaling of coordinates is x. Well, both y and z are invariant under a scaling of coordinates. So if we only had y and z, we would also have invariance under the de Sitter dilations, because there is no time appearing anywhere here, and this would be invariant under this. So we are invariant under the time dilations of the one of the symmetry of the Sitter, which is this time dilation one, which is you shift time and also rescale the coordinates. X, however, breaks this. So this is what allows me to deviate from the Sitter. And indeed, one can check that epsilon, this lower parameter epsilon, this is minus h dot over h squared, is actually equal to this derivative here. So as long as the derivative of f with respect to x is non-zero, but is small, then we can be arbitrarily close to the Sitter. So this is very good. So we can have inflation here, but also be not in exact exponential expansion. So how do we exit from inflation? So this, I mean, when we want to understand how to exit from it, we just want to see if we have some sort of like clock that literally tells us when to stop inflating. And we do have it, like in this model, because we can just look at, for example, this x variable or the volume of the determinant of the metric itself, which is essentially the volume. So these essentially track time, if you want. So they tell us when we can stop having inflation. And a toy example that the authors of this paper studied was this. This is a way in which you have instantaneous rating at some value, at some time, at some rating time. Before it, you have a generic function of x, y, and z. Instead of x, you can use the determinant is equivalent. And this gives you almost the Sitter with an epsilon that you fix. And after that, you go to a fluid case, more precisely a fluid, a perfect fluid with equation of state of radiation. I mean, this is a toy example that the authors came up with, but it's a way to show that you can just transition to the hot Big Bang in this scenario. So, okay. Now let's go to the Feramid case. Now, can we have the sitter here? Yes, I will show it now, but can we exit inflation? Can we have deviations a bit from the sitter? And I think the answer is no. Essentially because we just now, instead of having a clock, we don't have any clock here. We just have some frame at each point in space-time. So no regular way to know where to stop inflating. So if you wanted really this to be some model for the early universe and so on, you would have to augment this a bit with some other dynamics. But for me, this is not really a problem because here I was not thinking about constructing a model specifically, but just checking what are the interactions of the graviton. So from this point of view, it's still fine. Just look at this. So let me just quickly discuss why we can actually have the sitter here. There are many ways to show this, but they can be complicated. So to me, the simplest one is the following. Now, hopefully, is understandable. But essentially, I have a way to show that whatever object I write in the Lagrangian, I can always write it in such a way that it doesn't affect the action at the first order in fluctuations, which means that all the what are called tadpole terms in my action, they vanish by construction around the sitter solution. So this is by definition then tells you that on your action satisfy the equation of motion. The sitter solution is a solution of the equation of motion on the background. The fastest way to see this is that we can just look at all the operators that we can write, and this is actually very feasible to do because we can just look by doing some expansion in derivatives. So at zeroth order in derivatives, there is only one object we can write, which is this object here. We must contract the mu indices. We only have the metric to do it. We only have the tetrad, so we end up with this. This is some number. So once also the other indices here are contracted in a way that is rotational invariant, we just end up with some constant. And this is just a cosmological constant, which is fine. Then let's go to higher order in derivatives. And this is where things become a bit more difficult, but not so much, because we can have, for example, these objects take a derivative of the tetrad field, the time-like tetrad vector, or we can take some spatial derivative or some more complicated ones, so spatial derivative of the time-like component. You can do it, but the important thing that I wanted to emphasize here is that whenever you do this, you can always write it on the sitter, write these quantities on the sitter background in terms of objects that are either invariant at the local Lorentz transformations, like this. This is just delta mu nu. This doesn't carry any tetrad index, or objects that carry the tetrad itself. So you see here there is a tetrad, you have it here, and so on. So this tells you that you can always subtract these background values from your operators in such a way that doesn't need to introduce new degrees of freedom in the system. You just use the ones that you have, which is the tetrad H A mu A. And this is good. Then we can always subtract the backgrounds from your operators and without introducing new degrees of freedom, and then check that the tadpoles cancel. After this is done, in principle, one can check what happens to the fluctuations around this, but I won't discuss this. This is just to tell you quickly that you can have the sitter. Then let's go to the graviton interaction themselves. So now we have 3 cases to study. First, let me just quickly define what is the graviton. How we define the graviton here. So if the metric, the volume, sorry, not the volume, the line element, we have the cosmological coordinates, so scale factor, spatial ones, time, and the graviton appears in the spatial part as a transverse and traceless matrix, symmetric matrix. So what I wanted to show here is the following. First, I will check that it is enough. So all the 3 cases that we have to study, they are encompassed by the case of broken spatial diffraction fields. So there is the case of solid inflation essentially encompasses all the other ones. And then after I check this, I will look at a few interactions and just discuss a bit some phenomenology, just quickly. Okay, so let me start from the case of the effectivity of inflation of this superfluid case, where you break time diffraction fields. So now you're breaking time diffraction fields, so essentially your space-time was a preferred foliation that I show here. Now, what are the objects that you can write? These you essentially can write down either things that are depending on only on the geometry of the full space-time, or objects that depend on the geometry of sigma, or objects that depend on the way that sigma is embedded in the four-dimensional space-time. So the last two are expected to be some intrinsic curvature of sigma, or some extrinsic curvature of these hypersurfaces. For people that follow the GR lectures that we have every Friday, maybe the lectures of Elias, they also mentioned this split of space-time. This is essentially the same. So you have that the intrinsic curvature of these hypersurfaces will give you some curvature tensor that has gamma appearing with two spatial derivatives. Actually, you can think of some Riemann tensor on these constant time hypersurfaces. This has, we know that the Riemann tensor has two derivatives. They can only be spatial here. So you have this object. Instead, for the intrinsic contribution, the intrinsic curvature, you have that gamma appears with one time derivative. So there is nothing less than this that you can do in this case. Gamma must enter with derivatives, and this must be either one time derivative or two spatial derivatives. Okay, so this is the case of the effectivity of inflation of this superfluid case. So let's go to the feramid, type 2 feramid. First, let's see what happens at lowest order derivatives on zeroth order. Again, here as before, we cannot write anything at this order, because as we checked a few slides above, we checked that for the feramid, any object that I write without derivatives is just reduced to a cosmological constant. So there is no fluctuation there, nothing. So I cannot write gamma without derivatives in this case. Then let's see how I reproduce the results of the effectivity of inflation, and then if I have something more. So for the reproducing the effectivity of inflation, I just use the fact that I have also here some time-like vector that I can use, and this is the zeroth vector, the time-like vector of my tetrad, and this allows you again to write down gamma dot as before, essentially. And you can use this vector to construct this, all the objects that you had also in the effectivity of inflation. So you can essentially use this vector here to play the role of this, roughly speaking. Now there is something more, however, because now you can also use this the spatial part of the tetrad to write down gamma appearing with only one derivative, which you couldn't do before. Essentially, you can play around a bit with the indices and take some Christoffel symbols at the end, just taking one derivative here. And these Christoffel symbols, we know very well that the Christoffels have the metric appearing only with one derivative, and more precisely, when you take spatial indices everywhere, you end up with this quantity. So this is something more that you can do. Now then let's go to the case of solid inflation, or precisely broken spatial diffraction fields. So in this case, this is I will now show that this is where you have the most freedom of all. Essentially, the reason is that now we can have, first of all, now we know that gamma can appear also without any derivative. this you can see it immediately also from the solid inflation action itself, because now there are these objects appearing. These are just spatial metric, contracted trace, and so on. And these just contain the gamma by itself without any problem. So these for sure appear already here. Then let's see how we obtain the results of the other two scenarios. Now, differently from the case of the effective field theory, now before we had a slicing of space-time, now we had a threading of space-time. Essentially, the coordinates, the world lines of xi equal constant define some essentially threading of space-time. And whenever you have a threading, you can immediately write down the tangent vector to it. Essentially, again, using the volume form. There's always this trick of using epsilon. You can check that this vector here is normalized to -1 and is such that the xi functions are constant along the world lines of this vector. So by definition, this is the tangent vector to these lines here. Then once we have the tangent vector, then we are done, because we essentially can write down again an equivalent of the extrinsic curvature. More precisely, we can. This is something that is well known in, for example, when people do fluid dynamics in full relativistic setting. You write down a projector on the rest frame of these like observers, and from it you build you build this tensor here using derivatives, and this is such that if this observer were really hypersurface orthogonal, so they will define not only a threading but also like a slicing of space-time, this will literally reduce to what we call the extrinsic curvature. And so you can check that this quantity here again gives you gamma dot. And then you can take more time derivatives as you wish by using this this object here, just taking derivatives along this vector. What about spatial derivatives? This is again similar to the type 2 feramid, because you can again write down some sort of Christoffel symbols. This is a bit, there are a lot of fields here, but this is nothing else than essentially gamma kij, which I mean this is up and down, nothing less than that. Nothing more than that. The only thing that one must be a bit careful here is the fact that we want to be careful about not breaking this symmetry here, the scaling of spatial coordinates. We just want if you want the leading action to break this. So we just accomplish this by being careful at dividing every time by some appropriate power of the trace of the metric. And this makes sure that these vectors not spoil our symmetry that we had is in the minimal action. There is an additional difference here, which is the fact that now we have some indices that we can contract with spatial derivatives and time derivatives, and we can contract them. Before we could just use the delta ij, the Kronecker delta, to contract indices. Well, now we can use gamma ij itself, which you couldn't do before. We just use this object here. We just use gamma to contract these indices here. So this gives you even more freedom with respect to the other cases. So let me quickly discuss some phenomenology, because I see that I'm also a bit short on time. And then I will probably stop. So we've seen now that we can essentially, when we break spatial differences, as one probably would obviously expect, we can write essentially whatever we want. Then let me just discuss, instead of just looking at everything, just discuss some particular cases that maybe are interesting. I will discuss some cases by doing an expansion, as is usually in effective field theory, in perturbations and derivatives. And I will stop at a given order in derivatives, so up to order 2. And then we stop at cubic order in fluctuations. So this essentially allows me to describe, would allow me to describe the 3-level graviton by spectrum. So we've seen that from solid inflation, we have gamma appearing without derivatives. What are these terms that we get? First, we get a small mass for the graviton, which is suppressed in slow roll. So it's controlled by epsilon. But also we get some cubic interaction that is not suppressed in slow roll. So it depends on how F depends on Y and Z. So in general, this is not slow roll suppressed. So this is a purely local interaction for the graviton that gives rise to some non-Gaussianity that peaks in the squeeze limit, like essentially like FNL for like scalar non-Gaussianity that we are used to. And the size of these non-Gaussianity depends on the number of fifolds in this case. So this is something that has been studied already, but now we also have new interactions that enter at higher order in derivatives. Besides the second order in derivatives, what can we do? The simplest thing that one can think of when you try to modify the dynamics of some field is just change the speed of propagation of the fluctuation. Indeed, here you can also do this. There are many operators that can change the speed of sound of the graviton. But there is one interesting thing that one can see. Usually in the effectivity of inflation, when you have a superfluid and you try to change the speed of sound of the graviton, this immediately switches on some cubic interactions that have essentially carry the same coefficient as the speed of sound. So if the speed of sound goes to 1, interaction goes to 0, and vice versa. So in the effectivity of inflation, in this superfluid case, you can always say, oh, let me just redefine the light and just make some redefinition of the fields and have the gravity move with the speed of light, and all the interactions, then all the strange stuff is just dumped into the scalar sector. So I'm fine, then just have the graviton behaving as Einstein-Hilbert, so in the Einstein gravity, and just constrain the scalar part. So this is what's usually done there. This is why people don't really look at strong modification of speed of sound there, because there is not really any reason to do it. Here instead, this doesn't work because there is no univoc. There is not a unique tie between different speed of sound different from one and some interactions. You can just change them by themselves. So redefining the light tone would not change anything here. I mean, it wouldn't remove the interactions. So this is something that is different from the case of the effective field theory. And on precisely some of these interactions I write here, these are two derivative interactions, and I mean these are the tensor structure, and some of them, for example, this tensor structure here is contained in the Einstein-Hilbert part. So it just if you switch this on, you would just change the coefficients there. And also you can have something that doesn't appear in the Einstein-Hilbert, which is this one, which has 2-time derivatives and 3 powers of gamma. And also you see that that here gamma is appearing without any. There is a lag, if you want, that has gamma underived, and then this tells you immediately that also this interaction will lead to some non-Gaussianity that is peaking in the squeeze limit. So again, some kind of local non-Gaussianity for gamma. And finally, of course, this fact that you are having some non-Gaussianity squeeze limit means that you are breaking the consistency conditions for the gravitons and so on. I won't go into detail here, but essentially, this tells you that any kind of squeeze non-Gaussianity that you will get here is literally something that you can observe. So unlike what happens in the case of single field inflation. So I actually skipped this part because I see that maybe just go to the conclusions because I see that I'm a bit short on time. So we've seen now, let's go to the conclusions, and what are the conclusions? We've seen that essentially solid inflations, the breaking of spatial difference fields, captures all the possible interactions that I can have for the graviton in these scenarios where I'm breaking these isometries of the sitter. So what are some interesting things that one can look at after having found this result? So first one can classify more detail what are the possible operators and so on. but also it could be interesting to look for some regions of parameter space where you can enhance the tensor non-Gaussianities and modify strongly the tensor dynamics without also affecting the scalars and the other fluctuations. This is interesting to do because it is very difficult. This is difficult to check because it is very difficult to do in the case of single field inflation. You need to go to very high ordering derivatives there to actually try to find some combination of operators where you can play around and not touch the scalars. So this is one reason why, one thing that one could check in more detail. And also, I also will conclude by saying that it is interesting to look at this kind of enhancements at the level, by looking at the level of the Lagrangian, because again, in the prospect of this bootstrap approach, because I cite here this paper again by Enrico that says that essentially it is still difficult there to find some rules to tell you which kind of shapes of non-Gaussianity can be large. So working at the level of Lagrangian here can still give some help to find maybe some enhancement somewhere that is maybe difficult to see still at the level of this bootstrap approach. So essentially, this is what I wanted to tell you. And let me stop here, and thanks everyone for following.
Thank you. Just a quick announcement, we'll have more time for a follow-up discussion at 3 p.m. today. So just join at the same Zoom link as you joined this talk, and we can talk more, but we have about 5 minutes for questions right now. David, go ahead.
So still a kind of basic question, because my understanding of inflation is much more naive than this. So I'm trying to connect it to your language. So so I guess my question is, so when I think about inflation, there's the background, overall expansion. Then there's kind of quantum fluctuations on top of that background. And then there's also the quantum fluctuations getting sort of frozen in as kind of classical fluctuations in density or metric or whatever. Yes. And so my question is, is your description are these various descriptions of the background expansion, or are they predictions of the background and quantum, or predictions of this sort of fluctuated background after the quantum things have kind of frozen in?
The second one. So you would describe both the background expansion and the fluctuations, okay. The quantum fluctuations. So with a difference in the sense that with this kind of effective field theory approaches, you never try in some sense to solve for the background. This is something that actually is a big advantage, in my opinion, this effective field theory, when you can do it so precisely in this case. So you actually more precisely, you only look at the fluctuations. So instead of having like some potential, like you're having some scalar field with a potential and having to solve what is H in terms of the potential and so on, you just write down, you're able to write down an action immediately for the quantum fluctuation that then give you the observable, so the comoving curvature perturbation and so on. And all the interactions and the resulting non-Gaussianities of these quantum fluctuations are written in terms of some coefficients of effective field theory that are model dependent, but also the background quantities themselves, so H, H dot, and so on. So in this way, the background is there, but it's like you're very, very agnostic. So yes, but to answer your question, yes, you capture both of them.
Okay, so I should think of these as descriptions of the possible symmetries of the fluctuations.
Yes, yes, exactly. Yes.
All
You
right,
just use the symmetries to classify the fluctuations without having, without knowing what is actually that drives this, what is this like scale. For the case of the effectivity theory of inflation, you don't really care about what is the scalar, the inflaton, whatever. You don't, whatever it is, we don't care in some sense. We just know that there is something and then there are some fluctuations on top, and we try to describe the fluctuations. Yes.
Okay, thank you.
Matthias.
Yes, thanks. I had a couple of questions. So you started by looking at the symmetry patterns of the Poincaré. I think this makes sense, but is there a possibility that something is missed by this approach? That there's some other symmetry breaking pattern in the theta that is different? That's one. Yeah, I guess that's one question. And the other one, in terms of the phenomenology of the non-Gaussianities and this bootstrap, are these shapes that you have here? I haven't followed the literature, how far they've gotten. Are they able to predict this or like come up with these shapes already, or these are things that are surprising for them?
Yes. Okay. Let me answer maybe the second question first. I hope to make justice to the issue, because also to me I'm also a bit learning about this bootstrap. I'm not super expert. I would imagine this kind, for example, this kind of interactions here. I don't think they would, for example, they would be able to obtain them. I would think, because again, this involve boost breaking scenario, which so far has been studied, in my understanding, only in the case of a superfluid, if you want, which is not this. So I would imagine that you wouldn't still be able to get this kind of interactions here. But this is my guess, essentially because this is just another pattern that it's not been studied. So that should answer the second question. At least this is what I think would happen. One should have to extend the bootstrap to this like solid inflation case in some sense. For the first question, I don't know the answer, in the sense that my intuition was that you can. It made sense that you don't have something more, just because you should be able to go from the sitter group to the Poincaré when H is well, yeah, we're on very short.
When you're well inside
scales.
The horizon, right?
Yes, so that was my starting point. One should do another construction. To be honest, the literature on this is very, how do you say? There is not a lot of people that work on this at all, like this, from what I see. How you would do the construction, starting from the sitter case by itself, I literally have no actual idea how to do it. I think something is mentioned in this paper. In this paper here, there is actually a footnote where they mention what happens if the lambda, if you have a cosmological constant, but it's only a footnote. So my recollection of it. So to answer the question is that I don't know if there is something more. I would imagine no, because of what I said, but I cannot be extra sure.
Okay, great. I at least need to run. Let's maybe continue this discussion at 3 p.m. with anyone who wants to join. And thank you so much, Giovanni, again.